Joining me now is Henry Snaith, a professor at Oxford University. Thank you so much for being here.
Thank you for having me.
So to start off, why is photovoltaic solar energy emerging as a heavy hitter in the future of clean, sustainable power?
So photovoltaic solar energy is converting sunlight into electricity. They're the panels you see in fields and on houses. Basically, they've got very efficient and very inexpensive. So the cost of producing electricity from solar in the sunniest locations of the world is actually cheaper than any other source of power. So they're already cheaper than producing power from burning coal, for instance. They're completely green and sustainable, and there's a load of headroom to make them even better. So from here on in, they just get less and less expensive at producing power.
So in that vein, what's exciting about the role that metal halide perovskites could play in this future?
So I mentioned that the technology today is good, it's efficient, but it could actually be a lot more efficient. And perovskites have a possibility to really boost that performance and ultimately deliver twice as much power per square meter as existing technologies of today. On top of that, there's a big drive towards making all the materials even more sustainable. So for instance, a panel today might take about 5 months to 8 months to pay back the energy you put into manufacturing it, because there's a lot of heat goes into melting the silicon and creating the silicon. Actually, perovskites could overcome a lot of that and bring that down to maybe a month or something. So that's also a really important aspect of future technologies.
And these materials were discovered fairly recently. How have they stacked up against other photovoltaic cells in that short time? You kind of touched just upon that.
Yeah.
But.
So with the perovskites, so they were first realized in solar cells in 2009, so just over 10 years ago. And in that time, the efficiency improvements have been staggering. So today, just a single layer of perovskite is about the same efficiency as of the very best silicon cells, which were first introduced in 1956. So it's taken 70 years for silicon to get to the same place perovskites in terms of efficiency have got to in just over a decade. But what's really quite useful for perovskites, and something you can't do with silicon, is we can actually basically stack multiple perovskite cells on top of each other. I'll try not to go into too many details, but we can tune the band of light which they absorb, and that means we can absorb different parts of the sunlight in different cells stacked on top of each other, and this can deliver a much higher efficiency than silicon could ever deliver.
And you're mentioning a lot of great things, but what are some of the criticisms about using perovskites in solar power?
One of the criticisms is, or one of the uncertainties, is longevity. How long will they last? Solar modules are warranted for 25 years. In fact, there's a big drive in the PV industry to extend that to 35 and even up to 50 years warranty, because the amount of power you produce, the cost of that power depends on how long you produce it for.
Right.
Because perovskites are so new, we didn't even make any devices much more than 10 years ago. We haven't had the data and the learning experience to get to them to that same level of stability and prove it. So that's where the risk is. But of course, that's where half the effort's gone into making them more efficient, the other half's gone into making them more stable. And now in the research community, actually, activity towards really understanding and making these materials stable is where there's a growing interest and growing impact from the research.
And you kind of just touched on it once again, but should these critiques warrant skepticism, or really do the pros, it seemed like, outweigh the cons?
I'm obviously completely biased in terms of my view of whether perovskites are a good thing or not. The pros definitely outweigh the cons. There should be skepticism there because we need to address these things and properly, and not just saying, oh, it'll be okay, because it won't. We need to do thorough science, research and development to enable that to be okay. And that is going on, and that has gone on. And the progress that's been made in efficiency has been matched. In fact, in stability, the improvements are usually in orders of magnitude, so factors of 10 improvement. Time on time on time, this has happened. And they're very closely approaching the stability of silicon modules.
So what does the path toward widespread adoption look like for this particular technology?
So the path, there's multiple companies, tens of companies around the world working on this. Some companies sort of declare they've had some products, some early products launched. Other companies are launching products, this year, and other companies will be a few years down the line. What we're seeing is basically the early deployment of real commercial products now, They then spend time being deployed. Customers become comfortable with the technology. They know and realize that it does what it says on the tin, so then demand can ramp up. But what needs to happen is then manufacturing capacity needs to ramp. Similarly to silicon, this takes time. So it typically takes 3 years from specification to actually having a production line working. So we're going to see small scale deployment over the next few years, and then it'll be sort of 3 to 5 years before we start to get, you know, many gigawatts, and then beyond that, once it works and is proven, there'll just be a very rapid rise up to hundreds of gigawatts of production. That could happen this decade. It might be between 2030 and 2040.
All right, good to know. Thank you so much for taking the time.
Thank
Appreciate
you.
it.